All right, taking a look at improper integrals. That would be of any of these forms right here, where you have an infinity in one or both of the limit positions, or looking at these three examples right here. What makes this improper is that if the left limit or the lower limit 0 is plugged into the function, you have undefined situation. You have a vertical asymptote. Looking at this second example right here in this group of three, if you were to plug into the function 27 for x, you're again going to be dividing by 0. That makes that improper. And in this last example right here, what we can see is that this function is undefined at x equals 1, and 1 happens to fall between 0 and 3, so that makes this integral improper. And up until this point, we've only been evaluating proper integrals. You just didn't know it, but the problems we always encountered, the integrals we encountered, never was of one of these situations right here. Okay, so those are our improper integral examples. All right, so down here when you did this Explorer, I'm just going to record the answers that you may have gotten. Depending upon the kind of calculator you were using, your answer may have come out to be 2 ln 10 here. But if you use the green diamond enter, if you're using an 89, then you would have gotten this decimal right here, 4.60517. Okay, changing the upper limit to 1,000, traveling further to the right, but with the same function, you got 3 ln 10. Converting it to a decimal, 6.90776. And then down here, 6 ln 10, which I had 13.8155. All right, so going to the question, what do you think the value of this integral equals? Well, as suggested by the pattern, I'm thinking these numbers are getting larger and larger, slowly, but they are. So we're going to say that the value of this integral goes to infinity. So if the value of an integral goes to infinity, we're going to say that that integral diverges. It diverges. Okay, because it's not leveling off, it's not approaching a value. All right, let's look at the next couple of examples. If you were to evaluate this integral, I got the decimal 0.367879. And then even when I increased the upper limit to 1,000, I traveled further to the right and collected more region, area under the curve. I still got the same decimal. So what do you think the value of this integral equals? Well, I'm thinking it's going to be what I got right here. Okay, so in this case, we say that the value of this integral converges. It's leveling off to some particular number. It's not increasing without bound. So it becomes important for us to consider diverges and converges in this improper integral unit. So now let's sketch the graphs of these functions and shade the regions represented by these integrals. And it gives you a hint about the calculator setting for the window. Okay, so 1 over x. This is going to be on the first window setting. You see the reciprocal graph coming down like this, and remember that this is from 0 to 5, so it's a pretty small window for x, and then negative 1 to 2. Okay, and then it says sketch or shade the regions represented by this integral. So from 1, so if 1 is my input, then for x, then 1 is my output. So I guess that's off a little bit. It should be about, if this is the 0.11, and that can't be 2. So let me see if I can fix this graph. I'm going to try and fix it and lower it. Alright, let's see, that should be 1, 1. Okay. See if the screen's working here. So hopefully this is appearing. All right, so we've got this function right here. And so I'm supposed to shade the region represented by the integral. So that would look something like this right here. All this shaded region. And we're going to continue shading right here to the right, even though the graph of 1 over x is approaching 0. Okay, and if you change your window setting for this next description here of your x and y values, I don't know that you even see the y-axis, because if you look at the x scaling, okay, you're at 100, 500. So let me go ahead and remove this y-axis here. So now all you're going to see is the graph coming down something like this. Okay, and remember, we're at 100 to 500 along the x. Okay, and then the y-axis is really zoomed in here. So even though we're further out to the right, you can see that this graph is still not approaching the x-axis real clearly. I mean, it's not even touching the x-axis. So there's still a lot of space up here that's still yet to collect. So perhaps that's why when you think about the values we got previous, that this integral is what we call diverging. Diverging. All right, let's look at the second example. Let's graph y equals e to the negative x on the original window, the first one there. Okay, e to the negative x is going to be a decreasing function, decreasing exponential function that looks something like this. Okay, on the window 0 to 5. Well, if x is 0, then y is 1, so this is 0, 1. Okay, let's look at the integral 1. It's our lower limit, so if I plugged in 1, e to the negative 1, if you evaluated that, that's pretty small. It's about 0.36, so maybe the graph would come down a little bit further than what my picture shows here. Okay, let's shade the region represented by the integral from 1 to infinity. So that would be this shading right here. And I would continue, since this function doesn't actually touch the x-axis. Okay, so why do we have such different results? Why is this divergent and then this integral convergent? So let's change the window. And when you change the window, nothing shows up. Okay, we have this window setting 100 to 500. There's absolutely nothing there. Well, if you don't think the graph's there, hit the trace key. And when you hit the trace key, you can see that if you typed in 100, okay, that value, that y value that's reported back to you is an exponential number. If you rounded it, it's going to be 0. So if you continue to trace and maybe then hit 200, okay, that's even a smaller number, close to 0. So in fact, this graph, as the further you go out, especially from 100 to 500 along the x, you can't even see this graph. It's virtually the x-axis. Okay, so big difference between these two graphs here. So that would maybe lead us to believe that this one should be divergent and this one right here is approaching some particular space. I can find the area under this curve to the x-axis even though my upper limit goes to infinity. All right, so for this first page here, we just took a graphical approach to trying to evaluate integrals, but how do we actually find an answer? How do we evaluate these integrals? Okay, well, what we're going to do is we're going to rewrite these improper integrals as proper integrals, and then we're going to use limits and the FTC to help us evaluate them. So on the next page, if you turn it over, okay, what we have here is a rewrite. If we've established that we're going to be evaluating this improper integral, we're going to rewrite it with limits here. Notice what happened. I replaced the upper limit with infinity with b, but then what I want to do is I want to bring in the limit statement, the limit as b goes to infinity. Okay, for the second example, the lower limit was your infinity limit, so I'm going to replace negative infinity with a, the common practice a. So then I'm going to evaluate the limit as a approaches negative infinity. Here, and then this one right here would probably be the most complicated one because the rewrite has us using a limit of integrals. So right here we can see that this is a mistake and this upper limit should be positive infinity, retyping, I think I have everything changed, but you know, there's always something. So that's positive infinity on your copy. So what we do is we start with the lower limit of negative infinity, and we say, well, let's stop at some c value between negative infinity and positive infinity, and whatever that c is going to be up to us. We might want to make it 0, since 0 is a nice number to work with. But if I stop at c, then the next integral must begin at c and then end at infinity. So the sum of these two would give us back to what we have here. Okay, but these are still improper. And so then following what we did up here in example 1 and 2, these rewrites, we would take this first one right here and replace the lower limit with a, approach, and then bring in the limit as a approaches negative infinity. And in the second integral, we're going to replace the positive infinity with b, and then bring in the limit. Okay. All right, so you can, you know, kind of see right here that that would be the most involved one, the most tedious one. All right, so let's look at some examples of how we would actually find the value of these integrals without using the graphical approach as we did on the first page. Okay, so we're going to evaluate this limit, we're going to evaluate this integral, this improper integral. I notice that I have infinity up here in the b position, so I'm going to bring in the limit as b approaches positive infinity, and I'm going to rewrite the integral, make it proper, 1 to b. And 1 over x dx. Okay, so how we proceed is we find this integral right here, and then we bring in the limit last. So the limit is just kind of on hold for right now, but it does need to come through the problem as you're working through it. All right, this is a pretty basic integrand. I realize that 1 over x integrates back to the natural log of the absolute value, so that's what I'm going to put in here. Okay, so this would be the natural log of the absolute value of x. And I'm going to close my bracket here. And I'm going to take advantage of it and put my limits of 1 and b. So I still need to do the evaluation part, so that means limit as b approaches infinity has to come through. It doesn't disappear. We haven't done that operation yet. Okay, so in here I'll do the evaluation piece. So the natural log the absolute value of b, but I know b is going to be positive because if I begin at 1, I'm just assuming I'm going to positive infinity, so this b value will be positive, so I really don't need the absolute value, minus the natural log of the lower limit, which is 1, so the absolute value is not necessary. Okay. Alright, so let's do some cleanup in here. I know that natural log of 1 is going to go to 0. Okay, so to finish this problem, the limit as b approaches infinity is just going to be applied to the natural log of b. Alright, so if you substitute in infinity for b, what is the natural log of infinity? Well, think about the natural log graph. As x goes to infinity, the y values are increasing, not very much, but it's slow growth, but it is still going to infinity. Okay, so that confirms what we found through the graphical approach. So that's the answer for this improper integral. Alright, so let's see for the next example here. How we're going to find the answer that we got previous, which was 0.368, I think, something like that on the other page. Yeah, 0.367879. Okay, it's improper. Let's rewrite it as a proper integral. Okay, studying this right here, I don't have to do u substitution unless I want to. It's a pretty basic integrand. Okay, and that's actually going to integrate back to negative e to the negative x from 1 to b. Okay, now we have to plug in our limits. So let's bring forth the limit as b approaches infinity. All right. Right, so as a matter of fact, right here, this negative, I think I'm going to go ahead and manage it and bring it out in front of my limit here, just to unclutter the evaluation part. You can do that, bring out the constant, so that helps me kind of simplify this a little bit. So this becomes e to the negative b minus e to the negative 1. I'm not a big fan of negative exponents when we have to do calculations, so I'm going to rewrite this as 1 over e to the b minus 1 over e. Okay, and so now I'm going to continue. So this is the negative. So I still have the negative here. Now I'm going to go ahead and apply the limit. I'm going to plug in infinity wherever I see b. So I can drop the limit statement, so it's going to be 1 over e to the infinity minus 1 over e. And continuing to simplify, 1 over a super large number is 0. So we're going to end up with the opposite of negative 1 over e, so that's just 1 over e. Oh, goodness. And if you were to divide that out on your calculator, we should get the decimal that we got previous to the exploration activity on page 1. It's probably best just to leave your answer in this exact format right here. It wouldn't be wrong if you changed it to a decimal, but just remember you want to go to at least 5. Okay, so we're going to continue to practice evaluating improper integrals, but we're going to have to do it in the next video since we've run out of time here.